Okay, so let's get started. Welcome back. A week ago, we talked mostly about dot products and orthogonality. So I want to start with a review question and ask, what's the logical relationship between orthogonality and linear independence? Okay, great. Some good answers here. So I'll let Hardy talk about his answer. Yeah, that's great. So the picture I want you to have in mind here is something like this one. So last time what we talked about is that orthogonality implies linear independence. And visually, if you think about this picture, that's going to make a lot of sense. These three vectors are orthogonal to each other. So if you zoom it around so that one of them kind of disappears because it's pointing straight away from you or straight towards you, then the other two are going to be at a right angle. So you can kind of see this. I like to do this with my hand to kind of remember this concept of joint orthogonality or pairwise orthogonality, we should call it, where every pair of distinct vectors in the list is orthogonal to each other. It looks like this. And the idea is it's sort of like a souped up version of linear independence. Linear independence says you can't be in the span of the other ones. This stronger orthogonality condition says you have to be perpendicular to all of the other ones. And last time we also talked about this idea, which I want to review because I think it's a beautiful idea and it's worth remembering. How can we show that a non-zero vector, which is orthogonal to some other vectors, cannot be in the span of those vectors? Great. So this is an excellent start. We can show that the non-zero vector cannot be expressed as a linear combination of the other vectors. Right. So here's how that looks. The idea was to write out that condition in an algebraic form. So let's say a vector, let's call it Vn, is in the span of some other vectors, V1 up to Vn minus 1. This is what it means. There exists some coefficient C1, C2, and so on up to Cn minus 1, such as this equation holds. And then the idea was, well, let's dot both sides of this equation with Vn. And the left-hand side turns into the squared norm of Vn. And the right-hand side will just turn into 0, applying the linearity property of the dot product. Therefore, the squared length of the vector Vn has to be 0. And that only happens if it is itself the 0 vector. So this is a good illustration of how the algebraic properties of the dot product can intersect with and shed light on the geometric properties. So this picture you have in mind when you're visualizing pairwise orthogonal vectors, namely this one, conceptually it's clear that this should always be a linearly independent list. There's no way this blue one being orthogonal to both of these other two is going to be also in the plane spanned by the other two, right? But it's helpful to be able to show that in a way that makes it clear that it's not just a consequence of the geometric intuition here, which who knows how that applies exactly when you get into higher dimensions. It's an algebraic property as well, so it will always hold no matter how many vectors we have. Okay, so one other really important, perhaps most fundamental property of the dot product is the relationship between the dot product of two vectors and the angle, let's call it theta, between those two vectors. All right, so some correct answers coming in, I'll share. All right, so what we talked about last time is that u dotted with v couldn't possibly give direct information about the angle, because if you scale either u or v, the dot product will scale accordingly and the angle doesn't change. So there has to be some other relationship to accomplish that, to give us direct information about the theta. And it's the simplest one that works out. So you take the dot product, you divide by the norms of the two vectors, or rather you divide by the product of the norms of the two vectors. This is clearly not going to depend on scale. If you scale u by a given factor, you get that factor in the numerator and denominator, that's going to cancel. And this is going to be a property which is invariant under scaling. And so therefore it could possibly tell you something about the angle. And in fact, it does. It tells you the cosine of the angle between the two vectors. In any case, this is the key idea. U dot v equals norm of u times norm of v times cosine of the angle between the two vectors. Okay, here's still another question. And this one pertains to some data gymnasia content that we haven't discussed directly in class. So if you've gone through that content, you'll have seen it. You've hopefully also seen it before in another class. I want to just kind of give you a different angle on this. So here's the prompt. I want you to use this mathlet to try to find the inverse of this matrix A. So A is 1, -1, a half, 2, sorry, a half, -2. And you can apply this matrix A by adjusting this slider. So this slider says how much has A been applied, and it's really sort of mainly meaningful at 0 and at 1, but you see the values in between just for continuity for your eye. And you can control the matrix B over here. And when both dials are all the way up, the grid you see over here represents the composition of A and B. So anyway, I'll give you a minute to play around with that. It's trickier than it looks. And of course, you can get the answer another way. But I want you to just see if you can move these purple and green vectors around in such a way that you get back to the square grid over here. I'm going to do it with you because I don't really remember how it goes. And you can see that I'll have trouble with it too. Okay, so time is up. Folks are still playing with that. Some people had some pretty good ones. This one looks pretty good in a way, but if you look at it carefully, you'll see that it's not quite right. So again, the goal is to take the inputs here and get them back. The same value that you put in should be what you get out after you apply both of these maps. But you see what happens if we turn both maps off. All the grids are just the same. And then we apply this map, you see that it flips space around a little bit. Or rather, you see that it flips space around. And then when you apply this map, it doesn't perform a flip to get back to this square looking grid. This grid looks pretty close to this one, but it's got an extra flip in it that came from this middle operation because it didn't undo that. So this is not correct. I don't remember what is correct. I'll just use my script. Yeah, so one kind of trick here to make this easier is that if you can work it around to get approximately a correct looking square grid, then you can rotate both together, sort of rotate both by the same amount and kind of line up the grid with the axes. In any case, here's the actual answer. So this is going to be different than what I came up with a second ago when I was playing around with it. It looks like this. So if you apply both maps, I'll turn them both off. So if you apply both maps, this one flips around and stretches, and then this one undoes that operation. So it just basically reverses the movie. Starting from here, what this one does to both of them, this one just undoes it. So it takes a little experimentation to figure out what are the right places for the green and purple vector to go for B to invert A. And incidentally, you can do this in a number of ways. Obviously, this is not a good computational approach. This is about learning and kind of building up these mental models. If you want to do this for real, you have a variety of options. So you can ask Wolfram Alpha, which is a good way to go for these kinds of little problems because you don't have to remember syntax. It's right there on the internet. You can memorize the formula for the inverse of a general 2x2 matrix, which is not particularly hard to do and can be handy if you need to invert 2x2 matrices from time to time. Or you could use NumPy. So I'll show the NumPy operation here, and this will also give us a chance to go ahead and load our Python session. We'll just keep going with the lesson. I will say about this from numpy.linealg import inverse, you almost never want to do this. So if you're dealing with small matrices, like really small matrices, it's completely fine. It's about the same as anything else. But in the real world, you seldom have these small matrices dictating the systems that you're trying to solve. Or rather, when you do, it sort of doesn't matter what approach you take, it's all the same. What happens a lot more often is you have large systems of equations and you need to do things in an efficient way or you're going to get into trouble. And in numeric computing, the inverse operation is very expensive. And so this is kind of a truism in numerical linear algebra. It's one of the first things you would learn in a numerical linear algebra course. You don't want to be using the inverse function. Instead, you want to be using the function that solves the equation. So for example, in NumPy, that's the least squares function that we've already talked about. So numpy.linealg.least squares, or solve will also do the same thing. Solve is for situations where A is square and full rank. So the system is fully specified, it's got a unique solution. Then you can use solve. The reason we discussed the least squares function initially instead is that it's more generally applicable. Your matrix doesn't have to be square, it can be rank deficient, and it's still going to do something reasonable, something that you can comprehend for the way that it handles failures of either uniqueness of solutions or existence of solutions of the system you're trying to solve. But in any case, the linear system AX equals B is the kind of fundamental object from a numerical computing point of view. It's not, from a pure math point of view, it's easy to think about the inverse of A and kind of apply the inverse of A to both sides and get X equals A inverse times B. That's what you do in a linear algebra course. You don't do that in scientific computing. You keep A and B around, and then when you need the solution to the equation AX equals B, you call a solve operator. And the reason for this is, as I mentioned, finding the inverse is very expensive compared to just solving one of these systems. So even if you need to solve a lot of systems with the same matrix, it really has to be a whole lot of systems before it makes sense to actually pre-compute the inverse and store it. Okay, so dot products are useful for checking that vectors are perpendicular, but that's not a very constructive operation. You have two vectors, either they are or are not perpendicular, and it's like, well, what if they're not and you want them to be? What can you do? There needs to be some computational edge that the dot product gives you beyond just being able to verify something. And in fact, that's the case. And it's particularly useful in physics, which is where a lot of folks have seen this idea for the first time. It's applicable in lots of other areas of applied math, including data science, as we're going to see. So this is really sort of the central picture of the dot product. This is the main thing that it gives you. And will you be using this or sort of more complicated versions of this in a lot of different settings? So the idea is we have a vector u. So that's the teal vector here, which is not necessarily orthogonal to another vector v. So that's the red one. And what we want to do is replace u with this blue vector, which is perpendicular to v. And we want to do it in such a way that the span doesn't change. So in other words, u perp needs to be in the span of u and v and also perpendicular to v. So in this diagram, you can move the arrowhead around and you can see how u perp changes as we change u. And in fact, there's one additional property satisfied by this vector that isn't mentioned in this list, which is that you want it to be the same distance away from the line through v as u. So we're moving u as little as possible to get it to this vector u perp. So without that condition, u perp could be shorter than it is or longer than it is, or point the other direction. The thing that specifies exactly where it should be is the fact that the line passing through the head of u perp and the head of u, this line should be parallel to v. So a nice way to write this down, and again, we're going to get some very nice interaction between the algebraic properties that we can manipulate and the geometric properties where we can draw pictures and derive intuition. So we'll write it down like this. So we'll say that u is equal to u perp, so that's this step, plus something in the direction of v. So we want it to be the case that we can go some distance along the vector v and then add that to u perp and end up at U. So we're sort of decomposing U down into a V piece and a piece that's perpendicular to V. Sorry, this equation is wrong here. It should be U perp dotted with V is equal to 0. Of course, this angle is not 90 degrees. So it's supposed to be 90 degrees is the one between U perp and V. Okay, and the nice thing about writing down these equations is it gives us an actual formula pretty quickly. So you've seen this in the data gymnasia, but you might want to see it again here. So this is the same slide. All right, so suppose we have two vectors U and V, and we want to find a multiple of V, which is perpendicular to its difference with U. So in other words, we want to solve this equation. KV dotted with U minus KV, that's this blue vector, is equal to 0. So what do you get when you solve that equation? So I can see that I asked this one in an insufficiently clear way, because what people are doing is using the mathlet to solve it for this particular problem, which, to be fair, I often ask questions in that format. And that works pretty well here. You can get reasonably close just eyeballing and thinking about when is this angle 90 degrees. The goal here, though, is to solve this equation. So this is an abstract equation. All of these are just variables, and you can solve it for K. So I'll show you that. So what that looks like is V dots with U to give U dot V, that's there. The factor of K comes along for the ride. Then we have minus K times K, so that gives us a K squared, and then we have V dotted with itself. So that's the squared norm of V. And then we can solve this equation. You get this formula for K. So U dot V divided by the squared length of V. And we call this the component of U in the V direction, or the projection of U onto V. So you can think like, if I have this vector U and I want to project it onto V, just kind of smash it down onto V. Oh, that one doesn't move, sorry. You sort of smash it down onto V like this, then that vector that we get when we sort of squeeze it down like that, that's the projection of U onto V. So visually, you can think of projecting a vector as, the kind of this operation. Just move its head to the closest point along that vector. So I'm going to give you a few minutes to try to work this out for a specific example, because even though you're not going to want to do a ton of this by hand, it's helpful to see it kind of one time to appreciate how it works. So I want you to find two perpendicular vectors in R3 which span the column space of this matrix. And there are a variety of ways to do that, so I'll spot you another tip, which is to do what we did here. Leave the first one in place, just reuse this one, and then modify this second one in the way that we specified up here to make it perpendicular while preserving the span of the two vectors. All right, so this definitely looks like these two answers are along the right lines. Nick, why don't you tell us about how you came up with your answer here? Yeah, so that's exactly right. So what we want to do is dot the two columns and put that in the numerator here, and then dot the original column with itself and then divide. So we get -2/5 as our value of K. And then what we want to do is just do U minus KV, just like in the picture here. And that's going to give us our second vector. So we work out U minus KV. This is what it turns out to. So we have this -2/5 here. And so minus and minus becomes a plus, and you just work out the arithmetic component by component, and you get this vector. And if we want, we can double check that this is actually perpendicular to V. So we'll call it U perp here, and V is 2, -1, 0, just like we said, and we'll just dot them together. We can do that with the @ symbol, and sure enough, we get 0. So it looks like we did that in a reasonable way. Okay, so let's talk about the Gram-Schmidt procedure. We're not going to do this with a numerical example like the one we just did, but it really continues to work in the same way. So the idea is you start with some vectors and you want to sort of work through the list and orthogonalize them. So they may not be orthogonal originally, but each time you add a new vector to the list, you will want to subtract out its components in the direction spanned by the vectors that you have so far, and what's left over will be orthogonal to the vectors that you had. So for example, let's say you start with this red vector, and then you get some other vector which is in this blue plane, and maybe it's not perpendicular at first, but you orthogonalized it using the procedure we just came up with to get this orange vector, which is perpendicular to the red one. So we're kind of 2 steps into the procedure here. We've gotten 2 vectors which span this blue plane, and we've orthogonalized them. So they're definitely making a right angle with each other. And then we get this third vector, V3, and we're like, okay, we want to orthogonalize it. Clearly, it's not at a right angle with respect to the red and the gold one, making an acute angle with respect to both. And so what we want to do is kind of get rid of the component in the red direction so that it's only sort of, in the gold direction and the direction perpendicular to the two, then also subtract off that gold piece and end up with just this blue part right here, which is perpendicular to the plane. So that's the idea. We want to subtract off this part that extends in the green direction along this red line, and this part which extends in the gold direction. And then what will be left over with when we subtract off those 2 components is the orthogonal part. So I think I have a little illustration to kind of show. This one's static, and just took a screenshot and annotated it here. But these two black vectors are the components we want to subtract off. So we project onto the red one, we project onto the gold one, and then we subtract off each of those components in sequence, and we're left over with the perpendicular part. And that's exactly what we want. So this procedure is called Gram-Schmidt, and you'll often see this written out in terms of formulas. The data gymnasium content includes the formulas. I think the formulas are fairly hard to remember. It's helpful to see them once for sure, but the main picture you want in your mind, in my opinion, is this one. You're just working through the list, taking each new vector and subtracting off the components that it has in each of the directions of the previous vectors so that you get the part of it that's orthogonal to them. And that way you can work through a list of vectors which are not necessarily orthogonal, and you can orthogonalize them so that everything is orthogonal to everything else. Instead of getting into the formulas of the Gram-Schmidt procedure, though, what I want to do in class instead is talk about how it comes up in a data science context. And so I think this is really useful for motivating these ideas, because it's starting to feel maybe a little mathy, like how is this going to be interesting to me? So here's what I'm trying to develop to establish that connection. So suppose that we have some data that happens to fall quite close to some lower dimensional subspace. And what we want is like a nice way to represent that lower dimensional subspace so that we can stop thinking about our, let's say, 1,000 numbers that we have that specify for each data point where it lies in this 1,000-dimensional space. We want to come way down to, let's say, an 8-dimensional space, maybe because it just so happens that with 8 dimensions, you can pretty accurately capture the data set. And that's going to simplify our processing, maybe cut down on some of the noise in the data set. It could be useful for a variety of reasons. And let's say we want to do that. Well, we need some way to represent this lower dimensional space. Like, for example, imagine that I give you this set of points, which are orange colored here, and you actually plot them in 3-dimensional space, and you kind of look around, even without this plane here, which I've drawn, it wouldn't take you too long to figure out all these points actually lie really close to this plane. This plane is kind of the interesting variation within this data set, and there's just a little bit of variation in the orthogonal direction. So what you really want to do is effectively turn this picture like this and look at it head on from an angle where your line of sight is perpendicular to the plane. And then you're seeing really almost all of the variation exhibited by the actual data. The thing that you're suppressing is this other dimension, but there's not much variation in that direction. So this would be a nice thing to do. This is what you would do to actually look at the data set physically with this model to try to discern some patterns. Maybe if some of them were orange and some of them were a different color and you wanted to see what was going on with that. That's not the case here, although it kind of looks like it because some are in front and some are behind. But this gives you a feel for the data set that you don't have if you're looking at a worse angle. Like here, you definitely get less insight than if you look at it like this. So what we want to be able to do is actually come up with a representation for this blue plane here, or a higher dimensional analog of it, which is sort of more important because it's more realistic and you're going to get a bigger dimension reduction. And the way we want to do it is come up with some orthogonal unit vectors. It doesn't matter exactly what their angle is. The important thing is we come up with two vectors that meet at a right angle that span this plane. Once we do that, we can describe the data points in terms of where they fall on that plane after you kind of smash them down onto the plane. So let's suppose we have these two vectors there meet at a right angle and they have a unit magnitude or unit norm. So given some other vector, like one of these data points, what do you do to find the component of that data point in the B1 direction? So that has a simple representation in terms of the coordinates of U and B1. What is it? Excellent. So we had 3 answers. They were all perfect. We're going to, well, they're expressed in slightly different ways, but these are all morally correct. So what we want to do is dot the data point with B1. And that's going to tell us how much B1 we need to sort of reach out in that direction to get as close as we can within the span of B1 to the point U. And if we want to talk about the actual vector, we multiply that weight by B1. If we want to talk about just the weight itself, it wouldn't include that extra B1. But in any case, all of those are correct. And just to break that down, to say how we got there. So the K value, remember, we dot the two vectors, the one we're projecting and the one we're projecting onto, and then we divide by the squared length of the vector we're projecting onto. But the thing is, that vector has unit length because we decided up front, it doesn't matter really how long it is, we just want it to span the plane, or together with the other one, we want to span this plane. So we might as well make them have length 1 so that when we divide by the squared length here, there's nothing to worry about. We can just basically omit that operation. So that's telling us K is going to be U dotted with B1. That's how much B1 to use if you want to get as close to the point U as you can while being along the line through B1. And of course, no difference between B1 and B2. We're going to get the same formula for B2. So altogether, we can express the projection of U onto the plane, which means project onto both of the two vectors, B1 and B2, and then just add the results. So that projection is going to have this formula. We just dot with each basis vector, B1 or B2. So it's a basis of the space we're projecting onto. So we just dot with each one and then make that a weight for the corresponding basis vector. And that's our formula. So this is a nice, tidy representation of what it means to project onto a plane. So if I pull this picture up here back up again, the vector that we're going for is the one that goes from the origin to the base of this blue arrow. So that's the projection of the green arrow onto the plane. And you just get it by dotting with red, dotting with gold, and using those two results as weights for the red and gold unit vectors. That's going to give you the projection onto the plane. So in other words, it just says that the coordinates with respect to the basis B1, B2 are obtained by just dotting with those two vectors. So this is what makes working with orthogonal systems of vectors so nice. If we want to come up with coordinates, all we have to do is dot. There's no solving linear systems, coming up with some complex interactions between the different components. It's just one component at a time, dot with that basis vector, and then that's your weight for that basis vector. And that might seem tidy enough, but we can actually take it farther than that. So if B is the matrix whose rows are the basis vectors B1 and B2, then what matrix product represents these coordinates with respect to this basis? Yeah, so that one was maybe a little quick, but Nick got it here. So I'll ask Nick to talk about how he came up with that. So we just want to multiply b times u. Why is that the case? Great. Yep, that's right. So I'll show you this little picture with some colors to help illustrate what's going on. So if we, if you remember, this is how the matrix product works. One way we talked about thinking about the matrix product is that these are weights. These are weights for a linear combination of the columns of this matrix. But also, if you think about what that implies for a particular entry, this weight multiplies by this value, and this weight multiplies by this value, and the results add to give what you get here. And that's a dot product. So this row dots with this vector to give the corresponding entry that comes out. So that means that if we look at the matrix whose rows are the basis vectors, if we multiply that by a vector, that's just a tidy way of collecting all the dot products of the basis vectors with the vector u. And those are exactly the values we want. All the dot products are the coefficients that we get. So that's super tidy that we're not going to get any better than that. To project from a higher dimensional space to a lower dimensional one, if we have an orthogonal basis of unit vectors for the lower dimensional space, all we have to do is assemble them into the rows of a matrix, and then the matrix product is our projection operator. So I want to show you what this looks like looping back in with an example that we saw quite a long time ago at the very beginning of the linear algebra stuff. So I gave you these numbers. So this is 100 rows and 10 columns. There's 1,000 numbers here. And I told you, looking at these numbers in a table, you can't really see much. Like, it just looks like a bunch of random numbers. But in fact, we made the claim at the time that they all happen to lie close to a particular three-dimensional space. And we're going to talk about how to come up with this later, but for now, I'm just going to spot you the three-dimensional space. And I'm going to specify it by giving you a matrix whose rows span this space. So each of these rows in this matrix has 10 numbers in it. And together, these three rows, these three vectors that you see listed on these three lines of code, they span this three-dimensional space that we're claiming all of these length 10 rows up here are quite close to. We want to think about how to verify that that is the case. Let's go ahead and execute this block of code so that we have these basis vectors stored together in this matrix B. And I'm also going to give you the point. So this is a pretty big message. This is 1,000 numbers. So perform a matrix computation which produces the coordinates of the projections of these 100 points onto this 3D space. So you want to be projecting each point in this 100 dimensional, you want to be projecting each of these 100 points in this 10-dimensional space onto this 3-dimensional space. One thing that you might need that we haven't learned yet is how to do a transpose, or in other words, swap rows and columns in NumPy. And you do that just by calling the .t attribute on an array. So that will swap rows and columns. Okay, so let's walk through it together. I printed out the shape of B and the shape of original points so that we can think about this matrix product in a helpful way. So B is 3 by 10, and we decided that what we want to do is multiply B by some vectors, one for each point. So that means that those vectors need to be situated as column vectors in that product. We want to do B times the first point, then B times the second point, and so on. And given the way that matrix multiplication is defined, so matrix product is defined, what we can do is collect those different column vectors that we want to be multiplying B by into a matrix as columns, and then just perform the matrix operation, and that will tidily collect all of the operations that we're trying to perform into one single operation. So we want to be multiplying B by basically the original points matrix, but that doesn't quite make sense because the points we're interested in are rows in that matrix, not columns. And indeed, if we try to execute this line of code, then there's going to be a problem. It says that it doesn't match. But if we transpose it, then the original points become columns. And so we're doing B times the first column, give me the output as the first column of the result. B times the second column becomes the second column in the output, and so on. And that's exactly what we want. And indeed, this works. This is a little hard to read, so let's transpose it again. And that looks great. So we have 100 rows here, and each one is now 3 columns instead of 10 columns. So we reduced the dimension from 10 down to 3. And we want to try to figure out how much did we lose when we did that. If we want to check that the projections really are close to the original points, then I'll skip straight to the answer here. What we want to do is multiply the coordinates by B to see like where are the projections in that original 10-dimensional space, and then subtract off the original points from that. So if we run this code to get our coordinates, so the projections onto the basis vectors, and then we kind of pull that back up into the 10-dimensional space and then check how close that is to the original points, we get a lot of numbers that are really small, times 10 to the -4 times 10 to the -5. So as advertised, these points in this higher dimensional space, this 10-dimensional space, were actually close to this particular 3-dimensional space that we produced some basis vectors for. And that means that we can actually visualize this data set, even though it's 10-dimensional. We can project it down to this 3D space and then actually plot those triples of points in 3-dimensional space, and it looks like this. So we're actually looking at these 10-dimensional points, really. Each one has some small variation in those remaining 7 dimensions that are being suppressed, but not very much. So we're really looking at this 10-dimensional data set here in a meaningful way, even though we're only able to visualize 3 dimensions. So this is kind of, I think, the example I'd like for you to have in mind when we think about the value of projecting onto lower dimensional spaces using ideas of dot products. We want to be able to do this kind of stuff when we're doing data science. And that's all I have for today. That wraps up the linear algebra. So next time we'll start with calculus. Exactly. Okay. So the picture you want to have in mind for that is, yeah, that part was a little fast. I was definitely running out of time. The picture you want to have in mind for that is kind of like, well, actually this one is good. So there are kind of 2 ways you can think about this picture. So this teal vector is kind of the original data point here. It's the thing that you're trying to project onto a lower dimensional space. And there are a couple different ways you can think about this result after projecting. You can either think like, how much red and how much yellow did I need to get this projection? That's a way of storing that data with only 2 numbers, just how much red, how much yellow. And those are just dot products of the original vector's coordinates with the red coordinates and with the yellow coordinates.
Got it.
Or you could think, what's this actual vector that goes from here up to the base of this blue one? In other words, I need to take those 2 numbers I just came up with, how much red and how much yellow, and I need to say how much red times the actual red vector in R3. The how much yellow part, that scalar number, which tells me how long this arrow should be, or how, what the norm of this vector should be.
Right.
Multiply that by the actual 3-dimensional coordinates of the yellow vector, and then add the results. That gives me a vector in R3 that extends from the base here up to the base of the blue vector. And so you can think of this projection in either way, in the original space with the actual red and yellow vectors accounted for, or in the natural coordinates of this basis, or I should say just the coordinates with respect to this basis, which are just how much red and how much yellow. That's it. So in this picture down here, what's going on is when we come up with our coordinates, that's just saying how much red and how much yellow. And then there's actually a third one because it's 3-dimensional. So those 3 basis vectors that I gave you that are the rows of B, we're saying like how much of each of those do we need to add to get to the projections of the original points onto the space spanned by those 3 rows. But then if we want to compare to the original points, we can't look at those amounts because they're really specific to those vectors. If we want the actual projection to say like, is it really close to where it started? what we need to do is go back up into that higher dimensional space. In other words, we need to multiply by the rows of B again. So that's what's going on here. We do coordinates times B, and there are actually some transposes that are suppressed here. It's really kind of, in a sense, what you're doing is like B transpose times coordinates transpose, and then transpose all of that,
Okay.
which just works out to this. So it's, simpler to leave it like this. With all of these things, I think it's kind of tricky to really make yourself remember exactly how the transposes go, because it depends on, the conventions of how the matrix is written down. And it also is usually easy to just try something, and if it doesn't work, like transpose one of the vectors. Like look at the shapes and figure out what has to be transposed to make the matrix product even make sense. And then that's basically going to be right, because with all of these things, it's just some kind of a matrix product. So that's honestly kind of what I tend to do if I don't want to think through carefully, like which one gets to transpose, rows and columns, how does that exactly work out? I just look at the shapes and then form the only matrix product that makes sense. Obviously, that's not perfect, but it can be easier than, because of just remembering like which is which, rows and columns, which one gets transposed, which one
Right.
comes first, like that kind of stuff is not always easy to nail down. And it is easy to just like look at the shapes and figure out like what's the only thing that's actually compatible. We'll get into that in data 1010, but the short answer is it's using the singular value decomposition.
Gotcha. Okay.
So here, I wanted to set it up this way because once you see this big table and you're like, I don't know how to make heads or tails of this, and then all of a sudden you realize it can be visualized in a useful way, and you can reduce the dimensions from 10 to 3 to make everything much more manageable. And all you have to do to accomplish all of that is just somehow come up with these directions that allow you to perform those calculations and using these very simple matrix products. Then the value of this matrix starts to become pretty clear. You're like, well, however we came up with this B, that was some pretty cool stuff. So where did that come from? And it turns out you can develop this theory, which, it takes some time, and we're going to do the rest of it. So this sort of, is a good step in this direction already, what we've developed so far, but then we're going to do the remainder of it in data 1010. And the thing that we'll arrive at is something called the singular value decomposition. And it basically, from the point of view of the things that we're trying to do here, it's just, it feels like magic. You don't have to be creative in any way. You just compute the singular value decomposition of this matrix, the original matrix, so the matrix of original points. And it's just going to tell you exactly like, hey, these three vectors span a three-dimensional space, and here's kind of how much left over you have. And you can just kind of look at this list and see like, okay, I see that the first three grab a lot of the variation, and then the rest is just kind of noise. Or maybe in a real data set, of course, this is a synthetic data set that I've made up to illustrate this purpose. In a real data set, you'd have it sort of taper off. So you'd realize like, okay, the first 5 or 6 are quite prominent. And then, 7 through 10 there's still some useful information there that we're throwing away if we project onto the first 6 or 7, but, it's starting to fade. And then like after you get past, 20 or something, let's say, is really, really small, and you're just not throwing away very much if you reduce down by projecting onto those first, however many components. And so you can kind of play the trade-off how you want to. You can take some more components and throw less away, or you can take, you kind of get to do that trade-off however you want. So yeah, so bottom line, these row vectors here, which are kind of the magic to make everything work, they came from the singular value decomposition of the original matrix.